If we have a power of 14,490 watts, if we're working in a single phase, the formula is slightly different for a single or a triple phase, but it's always like this. Power equals U or V, that's the tension or the voltage, times the intensity of the circuit, times this cosine of P, that's a Greek letter, P. It's the power factor. Okay, so I don't know here because I haven't dealt with electricians in this country yet, but in Europe, everybody, okay, ¿cuál es el coseno of phi? What is the cosine of phi? Everybody is talking, all the electricians are talking about the cosine of phi, the cosine of phi. It's important because it's the power factor. Why cosine of phi? Because electricity, yeah, that's the explanation of the power factor. Okay, so we have two different waves. We have the wave of the voltage, and we have the wave of the intensity of the current. So we have to make these two waves as close as possible, because otherwise we are losing them. So that's a wave. So we are talking about this. We're talking about the real power and the reactive power. So that's the angle. Okay, so this is what we are losing. If this red line is very close to the horizontal, then we are quite good. If it's not close to the horizontal, then this we are doing something wrong. Okay, so and that's why we have this cosine. So 45, it's not acceptable. Yes, everything that is above 0.75 for this power factor is good. Okay. So that's why we have this explanation, because when we have to represent what's going on with these two phases that are not well connected, or we're not they are not lined up, these two different waves, when we represent this with this triangle, so that means that we are losing power, okay, because the real power is what we need, and the red line is what we are currently consuming. Okay, so there's something wrong. So the red line and the green line should match, and if that happens, this factor should be as close as possible. So you see that the power factor goes from 0 to 1. So if the power factor goes from 0 to 1, cosine P. So it's the same. If it's perfect, it should be 1. If it's so a value of 1 would be perfect. A value of 0 will be a disaster. Okay, because basically we are consuming energy, and that energy, that electricity, is not doing anything. Okay, so something that is above or greater than 0.75 is acceptable, but as close as 1, so 0.8 it's better than 0.75, 0.95 it's better than 0.8. Okay, so we have to make this close to 1. So if we know what the cosine of the angle is, if the angle is 0, cosine is 1. If the angle is 90, the cosine is 0. Okay, so when this red line is vertical, that means that we are not, all the electricity that we are wasting is not, doesn't have any effect. Okay, so that's why it has to be as close as 0. This angle has to be as close as 0 as possible. So this red line should be as close as the green line as possible. And that's the difference between the real power that we need and the apparent power. This is what we are really using. And the more the angle, the more energy we are losing in the process. So that's what we are doing here. Okay, so then we have to design the breakers. So we have the main switch or the main breaker. This will be for a single phase because we have 2 wires here, the phase and the neutral. So that will be the single phase breaker, and that will be a 3-phase breaker. We have 3 phases, 1, 2, 3, and the neutral. Okay, so depending on the size of the building, we have a single phase. Single phase for single family houses should be enough. In buildings like this, I'm sure that we have 3 phases. So there will be breakers like this. Then this is the miniature circuit breaker. Okay, so this is the breaker that controls every circuit. We have 2 wires, neutral and the phase. And then we have this one. It's the residual current device or differential circuit breaker. So this is, what is it? It's protection from leakage current against electric shocks for protection. Okay, so when there's a difference of charge or intensity between the phase and the neutral, if everything goes well, the phase and the neutral, the intensity should be the same. If it's not the same, this can cause problems. So when the system detects that these two, the neutral and the phase, they don't have the same intensity, that turns off immediately. Okay, so it's a protection mechanism. So that's why in a board, I like this better. So this is the main breaker. This is single phase because we have only 2, phase and neutral. This is the residual circuit breaker or the differential circuit breaker. So that detects difference of intensity between the phase and the neutral. And these are the circuit breakers, the mini or the miniature circuit breakers for each circuit. So those circuits immediately they turn off when the power exceeds the power for which it has been designed. Okay, so if I calculate that my lighting, artificial lighting circuit is 2 kilowatts, I design a circuit breaker for 2 kilowatts. If the power there is more than 2 kilowatts, it turns off. Okay, so everything is about protection here, because if we, or that happens with the sockets. Imagine that I have calculated that I'm going to plug 10 computers to the sockets. So 10 computers, each computer is 200 watts, times 10, it's 2000 watts, 2 kilowatts. Okay, but then I start turning a lot of things, and computers and our refrigerator, and so I'm exceeding the power, then it turns off. So it's a protection. So those breakers are for protection. If we can identify problems, we can isolate the problem. So if I want to replace a light bulb or something like that, I turn off the lighting circuit, and that's fine. But if I make a mistake and I start plugging or connecting things to that circuit, and this is something that human beings do. We need electricity, and it's pretty straightforward. We need that if we have a connection to the phase and another connection to the neutral, so I can if I know something about electricity, okay, what's the phase, what's the neutral? So I take this wire and okay, I connect something to the phase, I connect something to the neutral, and I know that I have power. So I can connect other things, but this is the lighting circuit and I'm connecting a refrigerator. Why would I do that? People do it. And then if that refrigerator has a lot of power and it's more than the power that it's connected to the lighting system, it turns off. So we are not electricians here. We only need to know the theory and how to calculate that. That's the formula for a single phase. We need to know the power, and we have this formula. The tension, if we are in a single phase circuit, the tension in the United States is 110, 120 watts. Cosine phi, it has to be as close as 1 as possible. 1 is almost impossible, but we can have 0.8, 0.9. And finally, we calculate the intensity. And the intensity is the size of this miniature circuit breaker. So if you have an intensity that is less than 10 amperes, that would be enough. If it's from 10 to 20, I would have to use a 20 ampere circuit breaker. So that depends on the power, that depends on the tension. The tension is given. If we're in the United States, it's usually 120. The power is something that I have calculated, and then I have to select the circuit breaker. It's quite easy. For example, this one. If we have an AC circuit, alternate current of 2500 watts with a single phase of 230 volts, that would be a European circuit, or even the United States. Remember, that's the three-phase. Okay, so that's the single phase in the US. In the US, we have 2 lines and 1 neutral. So the difference, the voltage between neutral and line, it's 120. The voltage between 2 lines, it's 240. This is because there are devices that in 120, they don't have enough tension, and we need 240. Why is that? I don't know. In Europe, we only have 1 phase and 1 neutral, and the voltage is always something between 220 and 240. Here, the default is 120, but you might need this. Anyway, in this problem, the tension is 230, and the power factor is 1. That's theoretical. We will never have a power factor of 1. But what is the circuit breaker? So the circuit breaker is like this. The intensity, we have this formula. We have to calculate intensity. So intensity equals power divided by tension and power factor. So intensity equals power divided by tension and power factor. The power is 2500 watts. The tension is 230. The power factor is 1. So the intensity of that circuit is 10 point. It's not 10, it's a point, amperes. And then we have to select the circuit breakers. So what are the circuit breakers? I think I have, yeah. So those are the commercial circuit breakers that we have in the market. It's 10, 16, 20, 25, 35, 40. Why those numbers? I don't know. But if our circuit is 10.86, we have to select a 16 ampere circuit breaker. 10 is not enough. So if we have an intensity that it's more than 16, because we have calculated this, if our circuit breaker is a 16 ampere circuit breaker and the intensity of this circuit surpasses 16, there's a safety, there's a fuse, and the circuit breaker stops working. Okay. The same thing here. For a 120 volt two-wire lighting system. Okay. what is the intensity? The intensity equals the power divided by the tension and the power factor. So if the power factor is 0.8 and we have 16 light bulbs or lamps, 100 watt each, so the total power would be 16 lamps times 100 watts. So that's the power, 1600. And then we have to divide this by the tension multiplied by the power factor. So it's 1600 divided by 120 times 0.8. So this is 16.66 amperes. So we have to go to the following one. It would be 20 amperes. So that's the circuit breaker. We have 10, 16, 20, 25, 35, 40, so on and so forth. Okay, so it's quite simple. What's the power? If we have a computer and the power of this computer is 200 watts, 200 watts. How many computers? 20 computers. Okay, so I need a circuit of 20 times 200. That would be 4 kilowatts. What's the tension? Is it 120 or 240? It's 120. Okay, so divide this. And what's the power factor? The power factor, we have to be realistic. And this is important. When the electricians are delivering the building, they need to test the electric circuits. And they calculate the power factor. They have a machine, so they connect the intensity, they connect so they understand the intensity, the voltage, they calculate the power factor. If it's about 0.75 or 0.8, okay, that's fine. If it's not, there is something that it's not well connected, and they have to review all the installation again. But this power factor, it's something that can be measured, and probably it's working well during the when they deliver the building, when the building is completed, but something can go wrong. And something can go wrong because of the users if we connect things that are not prepared. So if we connect things to a circuit that is not prepared for this device, there will be a problem. If there's a squirrel that eat the cable, there will be a problem. Okay, so there can be a lot of problems. So for maintenance, we should be measuring this power factor on a yearly basis, at least, because something can go wrong. And we can lose electricity. That's a problem because it's money. Or we can create problems, and well, depends on what we do or what the squirrel do. We can have some problems. Or anyway, calculating this, it's quite simple. And then we have to build this board with circuit breakers. If I need 1, 2, 3, 4 circuit breakers of 10, okay, and 1, 2, 3, 4, 20. Perfect. And finally, this is what we have to deliver. Okay, so if we have this schematic view for the HVAC system, and this is what we use to communicate with the mechanical engineer, we don't use the Revit file. This is the document that we use to communicate with electric engineers. It's an electricity schematic view. So what do we have here? We have all the miniature circuit breakers, and we name them. Oh, this is the bathroom and the kitchen. This is the washing machine and the heater. This is the kitchen, the electric kitchen, sockets and lights. In single-family houses, this looks. So we have a circuit for lights, another circuit for the sockets, the power sockets. If we have the kitchen consumes a lot of electricity, so we need a circuit for that. And then the washing machine and the heater, when they are both working same time, we have if they consume a lot, so it's better having a circuit for them. And then bathroom, kitchen, that can be for the water heater. So when we have a water heater, we usually have another circuit for the water heater. If we have an electric heat pump, we have another circuit for the electric heat pump. In commercial buildings, if we have the elevator, we have another circuit for the elevator. But in single family houses, that would be the minimum amount of circuits that I would design. If you don't have an electric kitchen, then you have an electric, you have a gas cooker or whatever. But if you have an electric oven, probably you will need another one for the electric oven. So there are things that are that consume a lot of energy, and so it's better to isolate that device into a single circuit. Then this is the differential, and usually we don't have to calculate anything else. This differential circuit breaker or residual energy circuit breaker, it's the amperes, it's always the maximum of the circuits that we have here. Okay, so if the maximum circuit breaker is 25 amperes, this is 25 amperes, and this is the differential, it's 30 milliamperes. So when there is a difference between the phase and the neutral more than 30 milliamperes, it disconnects that circuit breaker. And then this is the main, the general, or the main circuit breaker of the installation. And again, usually this value is the highest value of all these circuits that we have here. Okay, so this is how it works. If there's a problem, I don't know where the problem is, I disconnect this main breaker. If I know that the problem is in the lighting circuit, I disconnect this one, and the rest of them keep working. So this is the abstract version of this, or this. And you can tell if an electrician is good or bad because of the label. If you have a lot of wires, you don't know anything, basically. So it's not your job, I mean the users, not the architect, I'm talking about the user. If I receive this in my house, it doesn't look professional that the electrician let me find out what circuit is which. Okay, so let's look at this. Oh, that turns off the lights. What about this one? I don't know. Try to connect the washing machine. It's working. Try to, I don't know, use the computer. Oh, no, this computer is not working. So this might be, this circuit might be for the socket. It's not professional. So there could be labels. And everything should be very well distributed, and it's common sense. If there's a building like this, I don't know, I haven't seen the electricity boards of this building, but I'm sure that it's there is a common sense here. We have lights, first floor, lights second floor, sockets, first floor, sockets, second floor. There's a circuit for the elevator. There are another power sockets for probably the vending machines that are in the building. They consume a lot of electricity. So I'm sure that there's another, there are circuits for the classroom sockets, and there are other circuits for the machines that we have out there of the building that are not in the classroom. So I'm sure that there's a common sense, and it should be documented. And when we open the board, we should be able to identify what circuit is which. But it's not our job as architects, as users. We can, when we open the board, we can understand if the electrician or the electric company is good or not. If everything is clean, if everything is clear, that's perfect. If it's a mess and we have a lot of cables and we don't have any labels, okay, don't work with that company anymore. And examples. Fluorescent lighting fixture has ballast. The ballast, what is a ballast? A fluorescent light bulb. Are these fluorescents? I don't know. Now it's very difficult to tell, but when I was a kid, we were replacing all the light bulbs, the traditional light bulbs, by fluorescent lamps. And everything, where's the ballast? So the ballast is the element that connects the fluorescent lighting lamp or lamp to the electric current. Okay, anyway, that's the ballast. It's 180 watts. Determine the number of such fixtures that can be connected to a 2-wire circuit protected by a 20 amperes breaker, if the power factor is this. Okay, so that's another thing. This is the maximum power that I can connect to a 20 ampere circuit. So in this equation, it's always the same. Now I have to calculate the power because I have the tension, I have the intensity is 20 amperes, and I have the power factor. So if I have 120 is the tension. If it doesn't say anything about the tension, we can assume that in the United States, it's 120 by default. The intensity is 20 amperes. The power factor is 0.8. So this is 1920. And if we divide this by 185 watts, this is the maximum power that we can connect. If we divide this by the power of 1 lamp, so we have 10 powers. Okay, so we can go backwards, or if we have a circuit breaker, and we look at this circuit breaker, how many lamps can I connect to this circuit? Or it can be the other way around. I have 10 lamps and I have the voltage. So what is the maximum intensity? And then I have to select the circuit breaker. So I think we have explained that example. But it's always the main switch, the differential switch, and then different circuits. So by this time, I think the quiz will be open. And I'm going to do this one for you. So we have, so we have already done this, okay? So it's in the lesson. So we have this one, 185 watts per lamp. The circuit breaker is 20 amperes. The power factor is 0.8. And we don't say anything, the voltage is 120. If we don't say anything, the voltage is 120 by default. So this, all these quiz, it's like we're designing a house. Okay, so at the end, we have all these circuits. We have an electric kitchen, we have the lighting, we have the home electronics, we have the fridge, we have the washing machine, and we have the electric heat pump. So here we have the electric heat pump, here we have the washing machine, here we have the fridge. So we have been calculating the circuit breakers of all these circuits. So now that we have the total power and we know the amount of hours that each device is working, we have to calculate the price of the monthly electricity bill if we are running this for 30 days. Okay, keep going. And when you get to this question, if you don't know how to do it, ask me and I will help you. But first we have to calculate circuits, circuit breakers, and finally we have to calculate the price of the monthly bill.
Do you want decimals or just rounded?
What?
Like, but you can have,
you can have 10.5 lamps. It's either or 11. Sorry, no, one. Now, if the answer is 10.5, we can connect 11 because it's too much. We can run down.
Yeah. It's you. You put it to put in front of us, and you then fit it on the after what how do we get 10? Because I'm 185. How did you do the oh, you just no, you just kind of broke down the class. Yeah, it's fine. So you do those. You multiply the 16 and it's 1,600, yeah, 1,600. So you want to also, I have this one's 25 divided by I did get something like that there. Then 500 what the odds to the
Yeah, Mark. Oh, yeah, thank you. Yeah, so 1,100. Yeah, so it's all. Thank you. And okay. Maybe right. So it's what they is. Well, we just what we did this one earlier.